A warm good morning to all. In this lecture, we will discuss the magnetic behavior of an ideal Fermi gas. So, we will consider a system which is in equilibrium state and which consists of non-interacting fermions, and the system we are considering is in presence of an external magnetic field B. And our aim is to calculate the net magnetic moment M as a function of the external magnetic field B and temperature T of the system. Also to calculate the susceptibility chi of T. Susceptibility is actually a proportionality factor between the net magnetic moment M and the external magnetic field B. It tells us about the easiness of a material to get magnetized. For a given magnetic field B, if the net magnetic moment M attained by the system is high, then susceptibility is high. And if M is low for a particular value of magnetic field B, then susceptibility will be low. This susceptibility can be positive or negative depending on the direction of net magnetic moment M attained by the system. If the net magnetic moment is in the direction of external magnetic field, then chi will be positive and the phenomena is known as paramagnetism. If the net magnetic moment M is opposite to the external magnetic field B, then susceptibility chi will be negative and the phenomena is known as diamagnetism. The value of M and chi will depend on the intrinsic magnetic moment mu star as well as the degeneracy factor 2j plus 1. Okay, I will explain one by one. Now, in lecture number 14, that is in the lecture Statistics of Paramagnetism, we used the Boltzmannian treatment and we obtained a positive susceptibility since it is paramagnetism, and that susceptibility obeys Curie's law, that is at high temperature susceptibility is inversely proportional to temperature. Also at T equal to 0 a magnetic saturation occurs. Okay, as T tends to 0 we will have a magnetic saturation. But if you are applying Fermi statistics, the low temperature behavior will be significantly different, because for a Fermi gas we know that it is pretty live even at absolute zero. For Fermi gas, even at absolute zero, the particles are spread over a set of levels up to Fermi level. So the particles are distributed over a set of levels. But in the case of Bose gas, all the particles will be in the ground state. But for Fermi gas, there is a spreading of particles even at absolute zero. So the system is pretty live. So the behavior at low temperature will be different. There will not be any magnetic saturation, but we obtain a susceptibility value chi naught, which is independent of temperature but depends on the density of gas. So our aim is to treat the particle as a Fermi gas and prove that there will be a limiting susceptibility chi naught for T tends to 0, which is independent of temperature but depends on the density of gas. Pauli in 1927 explained this feeble and temperature independent character of paramagnetism in metals by regarding the conduction electrons as a highly degenerate Fermi gas. Okay, what is meant by highly degenerate Fermi gas? I explained in lecture number 29 and 30. Okay, now energy of a particle in presence of an external magnetic field B is given by E equal to P square by 2m minus mu star dot B. If the particles have no intrinsic magnetic moment, this term will not be there. particle will have only kinetic energy p square by 2m. But if the particles have an intrinsic magnetic moment, in presence of an external magnetic field, there will be an energy due to that magnetic field, and that is given by minus mu star dot b. Now, we are considering only spin half particles like electrons. Then mu star is either parallel or anti-parallel to b. If it is a spin 3 by 2 particle, there will be 4 possible orientations. For spin half particles, there are only 2 orientations. Mu star is either parallel or anti-parallel to b. So, we will have 2 groups of particles. Okay. Those having mu star parallel to b with energy p square by 2m minus mu star b. Why it is minus mu star b? If mu star is parallel to b, this dot product becomes mu b cos 0, and that becomes mu b. So, it is minus mu b. And the second group of particles having mu star anti-parallel to b with energy equal to p square by 2m plus mu star b. Because if mu and b are anti-parallel, this becomes mu b cos 180. Cos 180 is minus 1, and this becomes plus. So, we have only 2 groups of particles in the system. Now, we will consider the case of absolute zero temperature separately. Because for Fermi gas, at absolute zero, all levels up to Fermi level is completely occupied with 1 particle each, and levels beyond EF are empty. Okay, so the particle's energy must lie between 0 and EF at absolute zero temperature. Okay, so first group of particle will have their energy p square by 2m minus mu star b lies between 0 and EF. That is, kinetic energy will lie between 0 and EF plus mu star b. Second group of particle, energy p square by 2m plus mu star b lies between 0 and EF. Kinetic energy p square by 2m lies between 0 and EF minus mu star b. Once we have the kinetic energy of particles, we can find the total number of particles in each category. How can we find the total number of particles? You just find the total number of states by taking the degeneracy of states or density of states, and by integrating that. For Fermi gas at absolute zero, the density of states is equal to the total number of states is equal to total number of particles, because each state is filled with 1 particle, and all the states up to Fermi level are filled. So, the number of states will be number of particles. In order to find the number of particles, you just integrate the density of states. Okay. Now, what is density of states? We already know that, or we already derived this expression many times, and it is given by V by h cube. V is the volume, h cube is the limiting volume of phase space, into 4 pi p square dp. 4 pi p square dp. But p square is 2m into kinetic energy. So, dp is 1 by 2 root 2me into 2m, and it is square root m by 2e. Substituting that values for p square and dp, you will get this one. V by h cube 4 pi root 2 m raised to 3 by 2 e raised to half. And for the first group of particle, energy, kinetic energy varies from 0 to EF plus mu star b. So, integration should run from 0 to EF plus mu star b. If you integrate this, e raised to half dE, the integral will be e raised to 3 by 2 by 3 by 2. Substituting the limits, you will get the total number of particles in the first group, n plus, is equal to 4 pi v by 3h cube into 2m EF plus mu star b, the whole raised to 3 by 2. Similarly, the number of particles in the second group will be n minus equal to 4 pi v by 3h cube 2m EF minus mu star b, the whole raised to 3 by 2. Okay, there will be only change in this limit, and you will get this value. Okay, now the net magnetic moment M will be mu star. Mu star is the magnetic moment of one particle, and there are n plus particle which is parallel to the magnetic field, and n minus which is anti-parallel to magnetic field. So mu star into n plus will give you the net magnetic moment in the direction of field. Mu star into n minus will give you the net magnetic moment opposite to magnetic field. If two vectors are opposite, you can calculate the resultant by simply subtracting these. So net magnetic moment will be mu star into n plus minus n minus. Substitute the values of n plus and n minus. You can take EF outside this bracket, then you will get m is equal to mu star 4 pi v by 3h cube 2m EF raised to 3 by 2 into 1 plus mu star b by EF whole raised to 3 by 2 minus 1 minus mu star b by EF whole raised to 3 by 2. You can apply binomial expansion, retain only the terms up to first degree. Okay, terms of the order of mu star b by EF square you can neglect. Then this 1 and this 1 will cancel. 3 by 2 mu star b by EF minus of minus becomes plus. 3 by 2 mu star b by EF becomes 3 mu star b by EF. So you will get m is equal to 4 pi v by h cube 2m raised to 3 by 2 EF raised to half mu star square b. This is the net magnetic moment attained by the system. Okay. Now the law field susceptibility per unit volume is defined as chi naught. Chi naught, this 0 means we are calculating at absolute 0. And it is defined as limit b tends to 0. We are defining law field susceptibility, limit b tends to 0, m divided by Vb, because it is susceptibility per unit volume. That will be 4 pi mu star square 2m raised to 3 by 2 by h cube EF raised to half. Okay, simply divide this quantity with the Vb. Okay, this is the value. Also, we have an expression for Fermi energy from the previous lecture, lecture number 30. EF equal to 3n by 4 pi g raised to 2 by 3 into h square by 2m. For spin half electrons, this Landage factor g is 2. So EF raised to 3 by 2 becomes 3n by 8 pi h cube by 2m raised to 3 by 2. Or 2m raised to 3 by 2 divided by h cube is 3n divided by 8 pi EF raised to 3 by 2. Substitute this value for this 2m raised to 3 by 2 by h cube. Then you will get chi naught is equal to 3 by 2 n mu star square divided by EF. 3 by 2 n mu star square divided by EF. This is the limiting value of susceptibility. It is independent of temperature but depends on n, the number density. Okay. So Pauli explained the feeble low temperature paramagnetism by treating the electrons as a degenerate Fermi gas. Now, from lecture number 14, we know that at a high temperature, as T tends to infinity, this mu z is g square mu b square j into j plus 1 divided by 3 kt into h, where h is the magnetic field. And for spin half system, this Landage factor is 2 and j is equal to half. So this g square j into j plus 1 becomes 3. And the net magnetic moment m is equal to n, capital N, if there are n particles, capital N into mu z bar, that is equal to n into g square mu b square j into j plus 1 divided by 3 kt into h, and that becomes n into mu b square into this g square into j plus 1 becomes 3 divided by 3 kt into h, and it is n mu b square divided by kt into h. Okay, so m is equal to n v, because capital N you can write it as small n into v, mu square by 3 kt into b. Instead of h you can use a magnetic field, the letter as b. So chi infinity, this is at a high temperature as T tends to infinity. So we can denote it as chi infinity is limit b tends to 0 m by Vb, that is equal to n mu b star square divided by kt. Chi 0 is 3 by 2 n mu square divided by EF. So from these two expressions we can say that chi 0 divided by chi infinity is of the order of kt by ef, is of the order of kt by ef. Chi 0 is susceptibility at absolute 0, chi infinity is susceptibility as t tends to infinity. Now, the important difference between Boltzmannian treatment and Fermi gas treatment is, in Boltzmannian treatment, chi 0 is 0. If you recall the graph in lecture number 14, there is magnetic saturation. M becomes constant for low temperature because this is h by t. Okay, in this axis it is h by t. So low temperature means a high value of h by t. As the value of h by t increases, this m almost saturates. The value of m is constant. That means there is no variation of m with respect to external magnetic field, that is susceptibility is 0. But in the case of Fermi gas treatment, we got a susceptibility value even at absolute 0, and that susceptibility value is independent of temperature but depends on the density of gas. Okay, so that is the difference between the two treatment. Now we will consider the general case, that is for any temperature. Okay, so far we considered the special case at absolute 0, Now we will consider the special case that is applicable for any temperature. Here the particles can be above the Fermi level also. There is no restriction for the energy of particle, it can go beyond the Fermi level. So we will treat it differently. Consider Np plus as number of particles with momentum p and whose mu value is parallel to magnetic field, and Np minus number of particles with momentum p and mu value or mu anti-parallel to b. Okay, so again we have two category of particles. One is with the momentum p and mu parallel to b. Second one with the momentum p and mu anti-parallel to b. But this p can take different values. Okay, so there are a lot of particles. P can vary from 0 to any value. Okay, there is no restriction for this p. In the earlier case, there is restriction. Okay, the p value can be up to Fermi momentum, but here it can have any value. Now, particle will be there below and above Fermi level. Total energy of the system, En, we can write it as sigma p, sum over all momentum values, and for a particular value of momentum p, the energy is given by p square by 2m minus mu star b for this first group of particles, for mu parallel to b. And there are np plus such particles. For each particle, the energy is p square by 2m minus mu star b. There are np plus such particles. So you have to multiply that to get the total energy of first group of particles. For the second group of particles, the one particle will have energy p square by 2m plus mu star b. There are np minus such particles. So this is the total energy. But this is for a particular value of momentum. Then you have to sum over all momentum values in order to get the total energy of the system. Okay. Now, here this minus mu star b and this plus mu star b, this is independent of momentum. So you can take this minus mu star b from this term and this term, and the remaining is sigma p np plus. That is nothing but the total number of particles whose mu is parallel to b, and we can denote it as capital N plus. Capital N plus is the total number of particles with the mu parallel to b. It can have any value of momentum. The only condition is mu is parallel to b. N minus is total number of particles with the mu anti-parallel to b. Then this term and this term together can be written as minus mu star b into n plus minus n minus. Summation is not applicable for this term. We already did the summation. And the first term p square by 2m into np plus p square by 2m into np minus. That together can be written as sigma p np plus np minus into p square by 2m. So this summation is now applicable only for this first term. Okay. Now we will define the partition function. Partition function is actually the sum over all states exponential minus beta into total energy. Okay, sum over all states exponential minus beta into total energy. And here, what is the meaning of this primed summation? When though we mentioned that sum over all states, there are some restrictions for np plus and np minus. We are considering the system consists of Fermi particles. For Fermi particles, the number of particles in a particular level should be either 0 or 1. So this np plus or np minus should be either 0 or 1. Also, np plus, if you sum over all the momentum values, you should get capital N plus. np minus, if you sum over all the momentum values, you should get n minus, capital N minus. And the sum of this n plus and n minus will give you the total number of particles in the system. So this np plus and np minus should satisfy these two conditions. And this primed summation means it is a constrained summation which with the constraints, these two constraints. Okay. Now, in order to evaluate this sum in the partition function, we will follow this method. We will fix an arbitrary value for n plus. That automatically fixes n minus because the total number of particles is constant. If we fix n plus a particular value, then n minus will also be fixed. For that particular value of n plus, we will sum over all possible np plus and np minus. Okay, for a particular n plus, there are various possibilities for np plus and np minus, which gives you the same n plus. So sum over all that possibilities. Then sum over all possible values of n plus, which is actually from 0 to n. Okay, you can have all the particles anti-parallel to B, then n plus will be 0. You can have all the particles parallel to B, then n plus will be n. So this n plus can vary from 0 to n. So first you fix n plus and sum over all the possible np plus and np minus, then vary this n plus from 0 to n. That will give you the total sum. Okay. So we can write partition function equal to sigma n plus equal to 0 to n. This summation over np plus and summation over np minus exponential minus beta n. This summation over np plus, this double primed summation means restricted summation with np plus either 0 or 1 and sigma np plus equal to capital N plus. And this triple primed sum, again a restricted summation with np minus is either 0 or 1 and some sigma np minus is equal to n minus, which is actually n minus n plus. Okay, this is actually n minus. N minus is actually capital N minus n plus. Okay, so Qn is equal to sigma n plus equal to 0 to n. Substitute for En from this value En. Okay, if you substitute for En with the n minus as n minus n plus, you will get exponential minus beta mu star b 2n plus minus n, 2n plus minus n. This is actually n plus minus n minus, that becomes 2n plus minus n. Then sigma np plus exponential minus beta sigma p square by 2m np plus. Then sigma np minus exponential minus beta p square by 2m np minus. Okay, there are a lot of sums, so don't get confused. Okay, now consider a spin zero system. That is mu star is equal to 0. Then if we have a system of n spinless particles, what is partition function? It will be simply sigma np exponential minus beta sigma np p square by 2m np. This summation is actually not sigma np, this is sigma p. Okay, sigma p p square by 2m np. This is the partition function if mu value is 0. Okay, there are only one category of particle. There is no np plus, no np minus. Okay, there is only one category of particle. All are spinless particles. There is no magnetic moment. So the energy is simply kinetic energy. Okay, so momentum can vary. So total energy will be sigma p p square by 2m into np if there are np particles with a particular momentum p. Then exponential minus beta into total energy. Sum over all states will give you partition function. So this is the partition function of n spinless particles. And for denoting that spinless system, we have to add a suffix 0. Okay, q0 of n represents the partition function of n spinless particles. And again the primed summation means np is either 0 or 1. Again we are treating the system as Fermi system. So the number of particles in a particular state can be either 0 or 1. Also if you sum over all the np values, you should get total n. Okay, now we also know that free energy A, Helmholtz free energy A is equal to minus kT log q. From here q can be written as exponential minus a by kt, and that is nothing but exponential minus beta a. Beta is 1 by kt. And for a spinless system, you can denote this as q naught of n is equal to exponential minus beta a naught of n, where a naught is the free energy of the spinless system. Spinless system. Okay, for spinless system, we denote these quantities by putting a suffix 0. Okay, so we can write this summation is equal to q0 of n, and it is equal to exponential minus beta a0 of n. So in the summation here, in this summation we can modify this using this concept. You can write that as q of n equal to e raised to minus beta mu star b n into sigma n plus equal to 0 to n exponential beta mu star b 2n plus into q0 of n plus into q0 of n minus n plus. Okay, q0 of n plus and q0 of n minus n plus. Using this definition of q0 of n, if you substitute here for this quantity, then you will get q0 of n plus as well as q0 of n minus n plus. Okay, so q of n equal to e raised to minus beta mu star b n. You can include this to this exponential by using this definition for q0. q0 is actually exponential minus beta a0 n. So by writing q0 as exponential minus beta a0, you can combine together in a single exponential. Okay, here this factor only is in the exponential. These two are outside the exponential. So we can include that also in the exponential by using this curly bracket, by putting q0 as e raised to minus beta a0. So this becomes exponential of beta mu star b 2n plus minus beta a0 n plus minus beta a0 n minus n plus. Okay, if you take logarithm, log q is equal to minus beta n mu star b plus logarithm of a sum. Okay, logarithm of sigma exponential of this quantity, divide with an n, 1 by n log q is equal to this quantity. Now this logarithm of a sum, we can replace it by the largest term in the sum. Okay, this is a usual trick we applied in the statistical mechanics. Whenever you have a logarithm of sum, you can replace it by logarithm of largest term in the sum, provided the error is small compared to the term retained. Okay, in statistical mechanics, when n is very large, this condition will be satisfied. The error will be small compared to the term retained. Okay, so how can we find the maximum value of this quantity? By taking the derivative with respect to n plus and equate to 0. Okay, so when will this be maximum? You take the derivative with respect to n plus of that quantity, and when n plus is n plus bar, if this is maximum, then the first derivative will vanish. So take the derivative with respect to n plus and evaluate at n plus bar. Evaluate at n plus bar. That should be 0. Then you will get this as dou by dou n plus a0 of, this is the quantity you obtain, and in this consider the last term, dou by dou n plus of a0 of n minus n plus. This is dou by dou n plus of a0 of n minus. It is dou by dou n minus of a0 of n minus into dou n minus by dou n plus, using a chain rule. But n plus n minus is constant, total number. So dn plus dn minus is 0. So dn minus by dn plus is minus 1. So substitute here a minus 1. That becomes minus dou a naught of n minus by dou n minus. Okay. So replace this with this term. You will get 2 mu star b minus dou by dou n plus of a0 of n plus dou by dou n minus of a0 of n minus. These two derivatives should be evaluated for a value of n plus equal to n plus bar, and that is equal to 0. We also have the definition of chemical potential mu, which is dou A by dou N. Okay, partial derivative of free energy with respect to number of particles will give you chemical potential. These are standard definitions. Then if you apply here, you will get 2 mu star b minus, this is nothing but mu 0 of n plus bar, and this is nothing but mu 0 of n minus. Okay, and it is actually you can replace this n minus with n minus n plus, and it is also at a value of n plus bar. So this is mu 0 of n plus bar minus mu 0 of n minus n plus bar is equal to 2 mu star b. 2 mu star b. Okay. Now define a parameter r, which is n plus bar minus n minus bar divided by n. For paramagnetism, the number of particles whose mu is parallel to b should be greater than the number of particles whose mu is anti-parallel to b. Then only your total magnetic moment will be in the direction of magnetic field. So this quantity should be greater. So R is always positive. If you are dealing with the paramagnetism, this quantity R is always positive. Also, the maximum value of n plus is capital N. That is, then this n minus will be 0, and then this quantity will be 1. So R is positive and the maximum value of R is 1. We can say that R lies between 0 and 1. R lies between 0 and 1. Okay. Then what is NR? NR is n plus bar minus n minus bar. So magnetization is M is equal to mu star into n plus bar minus n minus bar, and that can be written as mu star into NR. Mu star into NR. From the definition of R, we can write it as 2 n plus bar minus n divided by n, and inverting this relation, you will get n plus bar is equal to 1 plus r by 2 into n. Similarly, n minus bar you should get as 1 minus r by 2 into n. Substituting these values for n plus bar and n minus bar, you will get mu 0 of, this is not mu 0 into, this is mu 0 of 1 plus r by 2 into n minus mu 0 of 1 minus r by 2 into n equal to 2 mu star b. Okay. Now, if b is equal to 0, if there is no external magnetic field, there will be completely random orientation of the individual magnetic moments. So the number of magnetic moments n plus bar and n minus bar will be equal, and r will be 0. There is no net magnetic moment. Okay, if there is no external magnetic field, all the magnetic moments will be in random. So parallel and anti-parallel will be equal in number. So r will be 0. If b is very small, r also will be small. Okay, if b is very high, then this r will tends to 1. Okay, if b is very small, r will be small. So we can expand mu 0 of n by 2 plus nr by 2 and mu 0 of n by 2 minus nr by 2 as a Taylor expansion about r equal to 0. What is Taylor expansion? If you are considering the Taylor expansion of f of y about y equal to y0, it is f of y equal to f of y naught plus y minus y naught f prime y naught plus etc. If you write a y is equal to y naught plus h, you can write it as f of y naught plus h into f prime y naught plus etc. Here, instead of y, the variable is here n by 2 plus nr by 2. So, about r equal to 0 Taylor expansion means the y naught value is actually, if you put r equal to 0, y naught is n by 2. N by 2. So, the Taylor expansion becomes mu 0 of n by 2 plus nr by 2 equal to mu 0 evaluated at n by 2 plus nr by 2 into dou by dou of n by 2 plus nr by 2. This is the variable. Mu 0 of n by 2 plus nr by 2 evaluated at r equal to 0 plus etc. But see this expression, dou by dou of ax plus b into f of ax plus b. If you have some function of ax plus b, then if you take the derivative and put x equal to 0, what is the value? F prime of ax plus b at x equal to 0 is simply f prime of b. And you can get the same value by taking dou by dou b of f of b. It is again f prime b. So these two are equal. So I will replace this partial derivative with this one, dou by dou n by 2 of mu 0 of n by 2. And if I write this 1 by 2 as x, then this becomes dou of mu 0 of nx divided by dou nx at x equal to half. Okay. Then you can take this n outside because this n is a constant. This 1 by n into dou by dou x of mu 0 of nx. You can write it like this at x equal to half. So replace this term with this one. This n will cancel with this n. So mu 0 of n by 2 plus nr by 2 is equal to mu 0 of n by 2 plus r by 2 into dou by dou x of mu 0 of nx evaluated at x equal to half. By neglecting all the higher order terms, this is Taylor expansion of mu 0 of n by 2 plus nr by 2. Similarly, for mu 0 of n by 2 minus nr by 2, you will get mu 0 of n by 2 minus r by 2 dou by dou x of mu 0 of nx evaluated at x equal to half. If you take the difference, you will get this as r into dou by dou x of mu 0 of nx evaluated at x equal to half. So substituting back in this expression, 2 mu star b is equal to this difference. So 2 mu star b is equal to r into dou by dou x of mu 0 of nx at x equal to half. So r is equal to 2 mu star b divided by dou by dou x of mu 0 of nx evaluated at x equal to half. Evaluated at x equal to half. Okay. So magnetic moment m equal to mu star nr. Substitute for this r value. Then you will get 2 mu star square nb divided by dou x of mu 0 of nx evaluated at x equal to half. So the law field susceptibility per unit volume chi is m by vb, and it is 2n mu star square divided by dou x of mu 0 of nx evaluated at x equal to half. Now we can this is the general expression. We can apply different special cases. For t tends to 0, chemical potential mu of n is 3n by 4 pi gv raised to 2 by 3 into h square by 2. And this is from lecture number 30. So mu 0 of nx. If you put 0, that is for the spinless system. Okay, if you put suffix 0, that is for spinless system. For spinless system, this g is 1. Okay. For spin half particle, this g is 2. For spinless system, this g is 1. And this is mu 0 of nx. So replace this n with nx. That is 3nx by 4 pi v raised to 2 by 3 into h square by 2. That is the value of mu 0 of nx. Take the derivative with respect to x and put x equal to half. If you take the derivative with respect to x, you will get this quantity. And by substituting x equal to half, this is 3n by 4 pi v raised to 2 by 3 h square by 2m 2 raised to 4 by 3 divided by 3. Also Fermi energy is 3n by 4 pi gv raised to 2 by 3 into h square by 2m. Our actual system is spin half electrons. So for that g is equal to 2. Then why we took g is equal to 1 here? For deriving this expression, In between, we assumed that if we have a system of spin 0 particles, then that quantities have to be denoted with a 0. And in that derivation, we use that concept. And the final expression is in terms of that quantity mu 0. Okay. So, whenever you have this quantity mu 0, for substituting that, you can use G is equal to 1. But you are calculating the magnetic moment for the actual system. So, the actual system consists of spin half electrons and you have to put G equal to 2. Okay. So, EF is equal to 3n divided by 8 pi v raised to 2 by 3 into h square by 2. So, chi naught is equal to, this is the value of chi. Here you have 2n mu star square. You have to substitute for this quantity. And that quantity is this one. But replace this 3n by 4 pi v raised to 2 by 3 into h square by 2m with 2 raised to 2 by 3 into EF. 2 raised to 2 by 3 into EF. And there is a 2 raised to 4 by 3 by 3. So, substitute here. That 3 will go to the numerator. Solving this, you will get 3 by 2 n mu star square divided by EF. Exactly the same result we obtained earlier. In the first case, we consider the case at absolute 0 temperature. There we obtained the same expression, 3 by 2 n mu star square by EF. So, in this general case also, if you put T equal to 0, you will get the expression. Now, for finite but low temperatures, okay, not 0 but finite low temperature, then the chemical potential mu is given by this EF into 1 minus pi square by 12 kT by EF whole square. If you put mu 0, that means that is for a spinless system. Okay, for a spinless system, this mu 0 n equal to multiply this with into this bracket. So, this is EF minus pi square by 12 kT square by EF. And for substituting EF, for spinless system, G should be 1. Okay, if you are considering mu naught value, then you have to substitute G as 1. So, mu 0 of n is equal to EF, substitute for EF, 3n by 4 pi v raised to 2 by 3 h square by 2m minus this pi square by 12 kT square into for this EF, you substitute this value. It is in the denominator, so this will be inverted. Now, mu 0 of nx, replace all the n with nx. Then take derivative. Take derivative with respect to x. That will give you this result. Okay, this taking derivative is very simple. This is simply power functions. And rearranging, you will get dou mu 0 of nx by dou x at x equal to half becomes 2 raised to 4 by 3 by 3. 3n by 4 pi v raised to 2 by 3 into h square by 2m plus this minus and minus becomes plus pi square by 12 k square t square divided by 3n by 4 pi v whole raised to 2 by 3 into h square by 2m into 2 raised to 8 by 3 by 3. Now, for the actual system of spin half particles, we have EF equal to, we have to substitute this value here, then we will get the actual susceptibility value, and for actual susceptibility value calculation, you have to substitute G as 2. Okay, so for actual spin half particles, EF is, Fermi energy is 3n by 8 pi v, not 4 pi v, 8 pi v raised to 2 by 3 h square by 2m. So 2 raised to 2 by 3 EF becomes this quantity. So substitute for this quantity also. Then you will get it as 4 by 3 EF plus pi square by 12 into k square t square by EF into 4 by 3. 4 by 3 EF can take outside. 1 plus pi square by 12 into kt by EF whole square. So chi is equal to 2n mu star square divided by 4 by 3 EF into 1 plus pi square by 12 kt by EF whole square. This 1 by 1 plus x becomes 1 minus x if you neglect the higher order terms. So for low temperature, you can neglect higher order terms. So chi is 3 by 2 n mu star square EF into 1 minus pi square by 12 kt by EF whole square. So this is the low temperature susceptibility chi, which is equal to chi naught into 1 minus pi square by 12 kt by EF whole square. If you put t equal to 0, you will get a 0 temperature susceptibility chi naught. Okay, for low temperatures, there will be a negative term. Now, for t tends to infinity, what will happen? For t tends to infinity, we know that fugacity z is less than 1. So, f of 3 by 2 z, f 3 by 2 of z, okay, this is Fermi-Dirac functions, which is approximately z, if z is very much less than 1. And we also have the number density n by v equal to g by lambda cube f3 by 2 of z. So, it is g by lambda cube into z, because f3 by 2 of z becomes z. Take this g by lambda cube to the left hand side. So, the z equal to small n lambda cube by g. Small n is nothing but capital N by v, number density. Also, mu, chemical potential is kT log z. So, it is kT log n lambda cube by g. Okay, our aim is to calculate dou mu by dou x. Okay, so we have to identify what is mu. So, mu is kT log n lambda cube by g. Again, we want to calculate mu 0 of nx, mu 0 of nx. So, replace this n with nx. So, kT log nx lambda cube by vg. Again, mu 0, this is mu, okay. For mu, you have to substitute g equal to 2. But for spinless system, mu 0, in our derivation, it was mu 0. Mu 0 of nx, you have to substitute g is equal to 1. It is kT log nx lambda cube by v. So, dou mu 0 by dou x is kT into 1 by nx lambda cube by v into n lambda cube by v. So, it is kT by x. So, dou mu naught by dou x at x equal to half is 2 kT. Substitute this value in the expression for chi. You will get chi infinity as 2n mu star square divided by this quantity. It is 2 kT. 2 will cancel. It is n mu star square by kT. Exactly the same expression we obtained using Boltzmannian treatment. Okay. So, this is the behavior of susceptibility as t tends to infinity. So, it obeys Curie's law. Now, for large but finite t. So, here we consider 4 cases total. One is t equal to 0. Second one is low temperature. Then t tends to infinity. Then large but finite t. Not infinite but finite. Then f of f3 by 2 of z, Fermi-Dirac function, cannot be written as approximately equal to z, but you have to retain one more time. Okay, the next approximation, z minus z square by 2 raised to 3 by 2. Okay, for large but finite t, you can use this expression for f3 by 2 of z. But n by v is equal to g by lambda cube f3 by 2 of z. So, f3 by 2 of z is equal to n lambda cube by g. Substitute here. So, n lambda cube by g equal to z into 1 minus z divided by 2 raised to 3 by 2. As a first approximation, neglect this last term and you write z as n lambda cube by g. And for actual getting the actual value, in the second approximation, you write this z as n lambda cube by g divided by 1 minus z by 2 raised to 3 by 2 and substitute for this z from the first approximation value. Okay, so this is the second approximation value. This is n lambda cube by g divided by 1 minus n lambda cube by g into 2 raised to 3 by 2. Using this approximated value, we will calculate mu. Mu is kT log z. So, it is kT log n lambda cube by g minus kT log 1 minus n lambda cube by g into 2 raised to 3 by 2. So, mu of n, capital N, equal to kT log n lambda cube by vg. Replace this small n with the capital N by v minus kT log 1 minus n lambda cube by vg into 2 raised to 3 by 2. So, mu of nx, replace all the n with the nx. Mu 0 of nx, replace all the g with the 1. Spinless system, mu 0 of nx, replace all the g with the 1. So, it is kT log nx lambda cube by v minus kT log into 1 minus n by v x lambda cube by 2 raised to 3 by 2. Take the derivative with respect to x, you will get this quantity. Put x equal to half, you will get 2 kT plus kT n by v lambda cube by 2 raised to 3 by 2 whole divided by 1 minus n lambda cube by v into 2 raised to 5 by 2. Take the LCM, you will get this quantity. In the numerator, this 2 will cancel and the final value is 2 kT divided by 1 minus n lambda cube by 2 raised to 5 by 2. So, susceptibility is 2n mu star square divided by dou mu 0 of nx by dou x at x equal to half. and it is 2n mu star square divided by 2 kt into 1 minus n lambda cube by 2 raised to 5 by 2. 2 and 2 will cancel. N mu star square by kt into 1 minus n lambda cube by 2 raised to 5 by 2. So chi is equal to chi infinity into 1 minus n lambda cube divided by 2 raised to 5 by 2. Actually this lambda not chi, this is lambda. Lambda is proportional to 1 by root 2. It is thermal de Broglie wavelength. So there in the denominator there will be a t. In the limit t tends to infinity, so this term will vanish. You will exactly get chi is equal to chi infinity. For finite but large temperature, there is this term also. So this is all about the explanation of paramagnetism of metals by treating the electrons in the metals as Fermi gas. Okay, so we explained the different regions. T equal to 0, low temperature range, high temperature range, and T tends to infinity. Okay, I hope it is clear. Thank you.